We have discussed so far single sample procedures, that is, when observations coming from a single population. But in practice, observations can come from 2 or 3 different populations. In this module, we shall introduce a new procedure which is called Mann Whitney procedure for comparing distributions when the underlying normality is questionable. We shall discuss Mann Whitney procedure or Mann Whitney statistic as a measure of degree of separation between two continuous populations, and using the analogy with U statistic, we shall derive some summary measures of the Mann Whitney U statistic. We have already discussed single sample problems like sign test and Wilcoxon sign rank test. We have also discussed goodness of fit problems and properties of these tests. However, we may have samples from different populations, and the concern may be to infer about the location or scale differences. In this module, we shall discuss a particular non-parametric procedure when independent observations are available from two populations. First of all, we consider a real situation. Suppose we have bulbs from two different brands, the old brand and the new brand. We have data on lifetime of the bulbs produced by these two brands. The data is given in the presentation. Then it is natural to know which brand is performing better. The usual practice is to use two-sample t-test, assuming normality. But normality assumption is not always reasonable. So, some exploratory data analysis will be helpful to identify whether the underlying distribution is normal. Now, we have data on two brands and we provide a normal QQ plot for each brand to justify the assumption of normality. Now, look at the QQ plot for the old brand data. The points are too distant from the straight line. However, if we look at the QQ plot for the new brand data, we find that most of the points are scattered very close to the straight line. In addition, we prepared a box plot for each brand to see the nature of difference. So, what we get? The QQ plot for the old brand data lacks normality, but the QQ plot for the new brand data reveals that the underlying distribution might be normal. Thus, we have one non-normal distribution and the others normal, and hence t-test is not appropriate. The box plot shows significant difference between the locations, but more or less same amount of variation. Since deciding an appropriate distribution is subjective, applying a parametric test is not reasonable. Thus, we need alternative procedures to judge the hypothesis. The underlying objective is always to know which brand is performing better. To get a reasonable answer, we first formulate the inferential problem. Suppose xi are n observations and yj are m observations. All are independent from distributions f and g respectively. Then the null hypothesis can be expressed as fx equal to gx for all x. The alternative is either one-sided or two-sided. The most general two-sided alternative is expressed as fx not equal to gx for some x. And the one-sided alternatives are either fx greater than equal to gx for all x with strict inequality for some x, or fx less than equal to gx for all x with strict inequality for some x. But what does this mean? If fx greater than equal to gx for all x, then probability x1 greater than equal to x is less than equal to probability y1 greater than equal to x, and this holds for every x. That is, y1 takes higher values more frequently than x. In other words, y1 is stochastically larger than x1. Similarly, fx less than equal to gx for all x implies x1 is stochastically larger than y1. However, setting an appropriate alternative depends on the dataset. For the given example, the objective is to know which brand is giving the more lifetime. That is, for which brand the lifetime is expected to be higher. Suppose x and y are respectively the lifetime variables for the old and new brand data. Then our interest may be to know whether the new brand gives more lifetime. That is, whether Y is stochastically larger than X. Thus, for the given data, an appropriate alternative should be fx greater than equal to gx for all x with strict inequality for some x. Now, if we look at the box plot of the two data, we find that the two datasets vary only with respect to location. Thus, we start with the assumption that the two populations differ only in location, so that we can infer about the difference in average lifetime. In particular, we assume gx equal to f x minus theta for all x, where theta is any value on the real line. Then fx equal to gx for all x is equivalent to theta equal to 0. Thus, the testing problem reduces to h0 theta equal to 0 against all alternatives. Now, we shall explain the difference in location through a plot of different distributions. Assume that the density function small fx, that is, the first order derivative of capital Fx, exists for all x. Then, we shall trace the nature of f x minus theta for different values of theta. Now, look at the plot below. The leftmost density corresponds to theta less than 0, and the rightmost density corresponds to theta greater than 0. Then, density corresponding to theta equal to 0 lies in between these two. Naturally, for theta greater than 0, the density is shifted to the right of that for theta equal to 0, that is, the observations corresponding to theta greater than 0 tend to be larger than those with theta equal to 0. Similarly, observations corresponding to theta equal to 0 tend to be larger than those with theta less than 0. Now, we shall formally define a statistic to capture the shift of the underlying populations. Suppose the x observations and y observations are mixed together and ordered according to their magnitudes. We have already observed that if theta greater than 0, then most of the y observations are likely to be greater than most of the x observations in the combined sample, and the converse is true for theta less than 0. Thus, the number of times an x observation precedes a y observation could be large in such a case. On the other hand, if theta less than 0, such a quantity could be small. This suggests to use the statistic u equal to summation I from 1 to n, summation j from 1 to m, indicator of xi less than yj for our purpose. The statistic u was suggested by Mann and Whitney and are often called Mann Whitney u. First of all, we need to know the extreme possibilities of u. The two possibilities are all the x's are larger than y's and all the y's are larger than x's. If all the x's are larger than y's, then u is minimum, that is 0, and in the converse situation, it is maximum, that is mn. For other configurations, u takes the values greater than 0 and less than mn. Thus, in all, we get 0 less than equal to u less than equal to mn for samples of size m and n. Now, we shall see how u measures the degree of separation of the two populations. We have already seen that u takes the extreme values if the two populations are completely separated, and with the well-mixed observations, u takes the intermediate values. The following figures will be helpful to understand these. Suppose we have 3 x observations and 4 y observations. We have prepared an individual value plot for both the populations. For the first figure, all the x observations are larger than those of y's and hence u equal to 0. In the second figure, we find 1x less than the highest y observation and hence u equal to 1. For figure 3, we find 2x's more than all y's and 1x is just less than the 2y's. In figure 4, we find 2x's just less than the highest y observation, and for these two figures, we find that the observations are getting mixed and hence making u larger. The next figure shows that a well-mixed pattern and hence u becomes larger. Now, if we look at figure 8, we find that most of the y observations are shifted upwards. Hence, most of the y values are higher than the x's and hence u is high as 11. For figure 9, all y observations are shifted upwards and hence the two populations are completely separated, making u a maximum. Thus, u is extreme when the two populations are completely separated and takes intermediate values when the observations are well mingled. Thus, u serves as a measure of degree of separation of the two populations. Next, we look at an important feature of u. If f equal to g, then the distribution of u does not depend on any f or g. That is, u is a distribution-free statistic. Note that under f equal to g, u can be equivalently expressed as the sum of the indicators of f xi less than f yj. Under f equal to g, fx1 up to fxm and fy1 up to fyn can be treated as m plus n IID observations from a rectangular population. Then, under f equal to g, u is a function of IID rectangular 0,1 variables. Thus, the distribution is independent of any f under f equal to g and depends only on m and n, that is, on sample sizes. Hence, u becomes a distribution-free statistic and therefore tests based on u are exactly non-parametric. Next, we shall derive the exact distribution of u when the null hypothesis is true. Naturally, such a distribution will depend on only m and n. Define PNMU as the probability that capital U takes the value small u under the null hypothesis, where small u is a number between 0 and mn. Now, arrange the n x observations and m y observations in increasing order of magnitude. Then, under f equal to g, each of m plus n choose n arrangements of n x's and m y's are equally likely. If NMU is a number of arrangements such that the number of x's preceding y's is u, then from the classical definition of probability, PNMU is nothing but the ratio NMU divided by m plus n choose n. Now, we shall derive a recursion relation for NMU. Now, in the arranged sequence, the last value is either an x observation or an y observation. If the largest value, that is, the rightmost value in the sequence, is an x observation, u is not altered. Then, the number of arrangements with the remaining n-1 x values and m y values with an x value as the last element, so that capital U equal to small u is n-1 m u. However, if the largest value is an y observation, it is higher than n x's. Then the n x values and the remaining m-1 y values will give u equal to small u minus n. Then the number of arrangements with n x values and m-1 y values with a y value as the last element, so that u equal to small u minus n is n m-1 u minus n. Thus, we get NMU is the sum of n-1 mu plus n-m-1 u minus n. Since PNMU is the ratio NMU divided by m plus n choose n, we get the following recursion relation. That is, PNMU equal to n divided by m plus n p n-1 mu plus m divided by m plus n p n-1 u minus n, where p n-1 mu is n-1 mu divided by m plus n-1 choose m and p n-1 u minus n equal to n-m-1 u minus n whole thing divided by m plus n-1 choose m-1. Note that small u is always non-negative and hence PNMU equal to 0 whenever u is strictly less than 0. Suppose n greater than equal to 1 and m equal to 0. Then we have only x observations and hence Pn0 equal to 1 if u equal to 0 and equal to 0 if u is greater than 0. Similarly, we have for every m greater than equal to 1, p naught m equal to 1 if u equal to 0 and p naught m equal to 0 if u exceeds 0. For small values of m and n, one can easily compute the distribution of u. Now, we consider few examples on how to use the recursion relation. First of all, note that for m equal to n equal to 1, u is nothing but the indicator of x1 less than y1. And indicator variable generally takes only two values 0 and 1. Thus, u for m equal to n equal to 1 has a Bernoulli distribution with success probability x1 less than y1. Under the null hypothesis f equal to g, x1 less than y1 and x1 greater than y1 are all equally likely. Therefore, the probability x1 less than y1 is half under the null hypothesis. And hence, u has a Bernoulli distribution with success probability 0.5 under m equal to n equal to 1. Next, suppose n equal to 2 and m equal to 1. Then u takes the values 0, 1 and 2. Then, using the recursion relation, we find that n210 is nothing but the sum n110 plus n20 minus 2. Now, n20 minus 2 equal to 0 as u is always non-negative. Again, applying recursion on n110, we get n010 plus n10 minus 1. And since n10 minus 1 equal to 0, we have n010 equal to 1 and we get n210 equal to 1. Next, consider n211, which is the sum n211 plus n20 minus 1. Since n20 minus 1 equal to 0 and n211 is again applying recursion relation, we see that n211 is equal to n011 plus n100, we get n211 equal to 1. Again, sum of the n-mn values is 3 choose 2, that is 3, and hence n212 is nothing but 1. Thus, probability u equal to small u equal to 1/3 for every u, that is, u has a discrete uniform distribution over 0, 1, 2. Next, consider the example with n equal to 2 and m equal to 2. Then, u has the possible values 0, 1 up to 4. Applying recursion relation, the distribution can be obtained, but what is important in these examples is the nature of the distribution of u, that is, the nature of the mass function. For the first example, u takes two values, each with probability half. For example 2, u takes three values, each with probability 1/3. For the last example, the middlemost value has the highest probability and the equidistant values from this highest value have equal probabilities. Thus, u has a symmetric distribution. Symmetry is in fact true for every m and n. This follows as below. Suppose f equal to g, then the distributions of xi minus yj and yj minus xi are the same for every ij. Then summation I from 1 to n, summation j from 1 to m, indicator xi less than yj have the same distribution as summation I from 1 to n, summation j to 1 to m, indicator xi greater than yj. Since summation of indicator xi greater than yj is nothing but mn minus u, we have under f equal to g, u and mn minus u have the same distribution. That is, u minus mn by 2 and mn by 2 minus u have the same distribution. Therefore, the null distribution of u is symmetric about mn by 2. Then, it doesn't matter whether we use the differences xi minus yj or yj minus xi while performing tests of hypothesis. Next, we shall see how u can be expressed in terms of the placements. Suppose we have n IID observations from fx and m IID observations from gx. Then define pj equal to n fn y ordered j, where fn is nothing but the empirical cumulative distribution function based on the x observations. That is, Nfn y order j is nothing but the number of x's less than or equal to y order j. Pj is called the placement of y order j among the x observations. Now, we can replace xi's by x ordered i's and yj's by y ordered j's. Then, summation I from 1 to n indicator x ordered I less than y ordered j is nothing but the number of x's less than equal to y ordered j, that is n fn y ordered j, or the placement pj. Then u can be looked upon as the sum of the placements. Next, we shall calculate first few summary measures of u. First of all, note that under the null hypothesis, u has a symmetric distribution and hence expected value of u under the null hypothesis is nothing but the point of symmetry, that is mn by 2. Next, note that u by mn can be looked upon as a u statistic with the kernel theta equal to probability y1 greater than x1. Then it is already proved in the discussion of u statistics that sigma square 10 is nothing but expected value of 1 minus gx1 square minus theta square, and sigma square not 1 is nothing but expected value of fy1 square minus theta square, and sigma square 11 equal to theta into 1 minus theta. Now, under the null hypothesis, x1 less than y1 and x1 greater than y1 are the equally likely events and theta equal to half. And in a similar type of calculation, we can find that sigma square 10 equal to 1 by 12 and sigma square 01 is also 1 by 12 with sigma square 11 equal to 1 by 4. Using these in the expression of exact variance of u statistic as we have derived in the two sample u statistic, we get variance of u under h naught is nothing but mn multiplied by m plus n plus 1 divided by 12. We have seen how Mann Whitney u statistic provides a distribution free measure of separation of two continuous populations. We have also derived the exact null distribution of such a statistic, but we did not provide some other properties like consistency, unbiasedness, asymptotic normality, or confidence interval estimation. We shall discuss all these things in our next module.